Okay. Hi, everybody. My name is Ben. I work at Booking. I am very excited to be here to chat with you about two very cool pieces of technology, Phoenix and RiakCore. So first off, some context. This is not a talk where I go, here's this amazing thing I've done in production, you should all do it, it scales, it's so cool. This is totally just me being really excited about some cool technology and how we can use them in cool ways. So that's it, just to set the expectation straight. Talk notes and code are going to be available. There's going to be a ton of content, so don't feel like you have to write everything down. It'll be there. And I would be delighted to talk about this stuff after the conference if anyone's interested in kind of chatting more. So okay, today we're going to build a stateful, distributed, fault-tolerant, real-time, impress your cat web application. Yeah. So we're not there yet. We just listed them. Okay, so first of all, let's talk about stateful. So what is a stateful web application? Well, it's pretty straightforward. It's just any web application that has some memory that we use in one request and then use it again in another request. It's pretty simple. But that's actually the weird thing to do. The much more typical architecture is a stateless architecture. So let's go over that real quick so we're all on the same page. So in a stateless architecture, in the beginning, there was the internet. And then we have some users come in, they hit a load balancer. They're randomly distributed over some app servers, usually running some Nginx and some application thing. And then those application servers hit a database for their data. They query, up you go. So this architecture has a bunch of really great advantages. One of them is that it's super horizontally scalable. We can just add more web servers if we need more capacity, and that's really effective. We know exactly where to find all of our data. There's one place we can do reports over our whole data set. It's really easy. SQL is the bomb. And that's really helpful. Our load balancing scheme is super straightforward. We can randomly distribute. We can round robin. Our load balancer doesn't need any knowledge of how our application is constructed, and that's really good. But there is one kind of slight drawback to this architecture, which is we don't do a great job of utilizing the memory on our application servers, by and large. Usually, in my experience, our application servers have enough memory for our application code and then whatever data the user needs in a given request, but not so much for things we might use from between requests. And so is that even a problem? Like, is it okay that we're wasting all this memory? Well, let's look at that. So this table is usually labeled latency numbers every programmer should know. I don't feel that strongly about it, but it is interesting. So this has been changed a little bit. So this GitHub user, Kofi Man, scaled it up so that the fastest operation is 1 second, a CPU cache reference. And everything has been scaled accordingly. So a main memory reference is 3.5 minutes. Yeah, OK, fine. Reading a megabyte sequentially from memory is 6 days. That sounds like a lot more, but I'm a scripting language programmer. Like, if my code is bottlenecked by reading data sequentially out of memory, I'm like, yeah, my code is fast. That's awesome. OK. So doing a network round trip in the same data center is 11.5 days. Like, OK, that's fine. And then reading a megabyte sequentially from disk is suddenly, whoa, like 460. Like, that's so long. That's forever. And so as high-level language programmers, there's not a lot that we can do to manage our cache hit rate or our main memory reference, how much often we hit that. But we might be able to change our architecture to do more reading from memory and do more round trips, even if it involves doing more round trips, that is. So this is kind of what Jose was talking about with Moz, where they moved away from having a database entirely, and they kept their whole data set in memory. So that's the kind of thing we're going to talk about. And so how does that work, trying to leverage memory in a stateless architecture? Well, the thing about this layout is that basically the memory that we can use really easily lives in the database tier. We can add caching like Redis or Memcached, but by and large, the thing that's totally simple, if I want to have more of my data in memory, I buy a bigger, faster, better database server, right? And so given this constraint, why is it that our applications are almost always structured this way? Like almost every web application typically is a stateless architecture. And so one reason is our workload. Stateless protocol, stateless architecture kind of checks out, right? But I would argue there's more of a historical, like a toolset constraint on why we do it this way. And it has to do with the scope of memory reuse in our applications, in our web applications. And so one of those is our programs are short-lived. Back in the day, it was CGI. It only lasted for the length of a single request. These days we have workers, but still the lifetime is kind of arbitrary. They usually terminate after a particular number of requests. And from others' perspective, that's basically a random termination. Even when we do have long-lived programs, like we're using an event loop, Node.js, event machine, any event, something like that, the scope of memory reuse is still limited to a single core. Event loops typically are single-threaded. And then finally, even if we do something to coordinate between our different threads so that we have memory use on a single server, coordinating between servers is really challenging. Like maybe you could do something funky with 0MQ or something, but that's very non-standard. And so how much do these constraints apply to us building applications using Elixir and Phoenix? Well, so the first thing with the workload, like, yeah, we do a lot of HTTP, but browsers have WebSockets now, and we have channels, and so maybe more of our workload is shifting in this stateful direction. I'm like, okay. In terms of memory reuse, short-lived programs, well, I'm pretty sure there are Erlang programs that have been running for 10 years. I wouldn't be surprised. So that's not really a thing. We're using the Erlang VM. Single-threaded program, same thing. We're using the Erlang VM. It does that for us. And then finally, the kind of most magical thing about the Erlang VM, the distribution, we can coordinate between servers kind of transparently. So great, let's do it. Let's build a stateful web application, right? So okay, so what does this look like? We have 2 physical servers, not gen servers, right? And they're running Phoenix or something, and maybe we want to store some data on them, so we're going to use some ETS tables. Just keep the data in memory. And so let's say we put data for user 42 on server B, and we don't have anything on server A yet. So user 42 shows up. They want to use our application. Now we have a decision to make. We could do some kind of complicated, tricky load balancing, like sticky, and attach them to server B. Or our load balancer could be magically aware of our data layout. But that's complicated, and we're using Elixir. So we'll route them to server A and just have them ask server B for the data. Server A will look for it and say, I don't have it. Like, OK, server B. We can send to a PID on server B. That's easy. We can do gen server call or cast if we're feeling OTP-ish. And I'm done. So I have a distributed stateful web application. I have a lot of time left, but maybe not, right? So when we think about how this approach is going to grow, we start looking at something like this kind of terrifying spider web of logical connections. Like, this isn't the mesh that the Erlang VM generates. This is just servers requesting things to each other. And we find ourselves firmly in the realm of distributed systems. And this is kind of a scary world, but we're going to go there. So that's what we're talking about with a stateful web application, storing some data on the node. But it turns out coordinating state between different servers is really challenging. So let's look at how we can distribute it. So here's what I want to say about distributed systems when it comes to cross-node sending or gen server call or cast to remote PIDs. They are the equivalent in distributed systems of print div in web development. That is, they are absolutely foundational. You have to have them in order to have a web application. But it's the very base thing, right? And so building a distributed system out of ad hoc message passing or RPC is like writing a web application that kind of goes like this, right? A MySQL query, my cool query, and stuff it in some HTML, and echo it out, we're done. Yeah, right? And so I don't want to say this PHP is bad, because we have all written this code. And moreover, it has generated fantastic amounts of value. That's why there's all the dollar signs in the language, right? Like this. So this generates value. It solves problems, just like ad hoc message passing. But at the same time, we have, as web developers, kind of converged on a more structured way of building our applications. We've converged on model view controller. And so that kind of brings us to a question: what is the model view controller equivalent when we're talking about designing a distributed system? And so, okay, you think MVC. I've heard another 3-letter acronym when it comes to distributed systems: CAP, C-A-P. Consistency, availability, partition tolerance. And so I'll define them real quick. Consistency: if I ask 2 servers a question, do they give me the same answer, or does one of them out of date, or is it diverged or something? Availability: if I find a server that's working and I ask it a question, is it going to give me a good answer, or will it say, sorry, my friends are unhappy right now, I can't help you? And partition tolerance, which is how well I can deal with network partitions. So okay, and then the general formulation for when we're using this thing to talking about our trade-offs is pick 2. Okay, fine. But when we're approaching this as a way to design or structure our distributed system, it is not helpful, right? This doesn't help us design something. It doesn't tell us how to structure our communication. But that's okay. That's not really what CAP is about. CAP is about having a discussion about trade-offs. And our trade-offs kind of fall into these different buckets where we pick 2. And so you've got consistency and partition tolerance. It's kind of questionable if you actually can have consistency and availability because there's always going to be network partitions. But today we're going to talk about things that fall into this bucket, into the availability and partition tolerant kind of end of things. And we're going to talk about concrete patterns that could be classified this way. And so what are some of those patterns? Well, there's gossip protocols. So like I'm server B and I talk to server A and I go, psst, I've got user 42's data. If you tell any of your friends that I have the data, so if they need it, they should come to me, right? And then your information kind of spreads virally. Conflict-free replicated data types like Chris talked about with Phoenix and Presence, and those are really cool. And then there's this other thing, distributed hash tables. And they're a mechanism where you can take a big body of data and split it into smaller chunks and have different chunks on different servers. Well, that sounds pretty good if what we want to do is take a big data set and keep parts of it in memory around our whole cluster. Like, that's kind of promising. So great, let's do it. Let's build a stateful distributed web application using a distributed hash table. So the first thing we should do is not reinvent Rails, not reinvent Phoenix, but find some implementation of this pattern that we can leverage to build our application. We're going to make fewer mistakes. It's going to be a better experience. And so that brings us to RiakCore. And so RiakCore, the thing on the README, it's a toolkit for building distributed, scalable, fault-tolerant applications. OK, fine. All right, let me lay down some hype. It is mind-blowing advanced technology, OK? This is really cool stuff. And it basically doesn't have any peer in other platforms in terms of maturity, in terms of the features it offers. It's really cool. Like, it's amazing. So, and we can use it because we're Elixir programmers. This is an Erlang thing. Like, this is cool. OK? So let's talk about how it works. So this is the slide you see in every single, like I had to do this, I'm talking about Riak, you see the ring, right? And this is, different colors, different servers, but this is kind of overwhelming at first. So let's back off. Let's talk about a plain old hash table, like in Ruby, like in Perl, like in Python, right? And so hash tables, you all probably know, they're backed by an array. Let's say our array has 4 slots. They're usually called buckets when it comes to hash tables. And so when we want to put something into our hash table, assign 42 to the key answer, we hash our key, and we get some number. It doesn't matter what the number is, really, it's just some number. And we take that number, and we run some transformation on it so it will fit into one of our buckets. In this case, the transformation is the length of our underlying array. And then, OK, now we know where to put our thing. We put answer in index number 3. Great. So a distributed hash table is very, very similar. Same exact operations, except different servers own different buckets. And so in our case, server B owns the last one. And so if we need to look for this data, we know we need to go to server B. Cool. So let's look at this slide again. And so the main thing is just a question of vocabulary. When Riak says vnode or partition, what they're really talking about is a sequence of buckets that are all in a row in our underlying array. And we've taken our array and we've kind of wrapped it around into a circle. But that's it. And so when it says a single vnode, that just means responsibility by an Erlang process for a series of buckets. We're going to put stuff in those buckets, and when we hash to a certain value, it goes to that vnode. So that's it. So let's build an application using RiakCore and Elixir, just to get a feel for things. So we're going to build something really simple. We're just going to send ping requests to different parts of the node, different parts of the cluster, excuse me. And so ping, pong, that's it. That's the whole thing. We're going to hash the timestamp so that every time we ping, we're going to get a different hash value, and it's going to go somewhere else in our cluster. Okay? And the destination is going to be a vnode, or one of those hash buckets in our kind of underlying array. And so this might sound like kind of a trivial example, but really it's a good example of distributing CPU work around our cluster. So imagine I have this cluster and it can do different jobs, and I want to have certain workers handle certain jobs. Well, a vnode could be responsible for one class of job. So what are the parts in a RiakCore application? There's a service, which is kind of your high-level API. This is how people are going to interact with your application. You have a vnode, where you implement your business logic. And so like I said, a vnode is just a hash bucket with some code attached. That's the whole thing. There's a supervisor and an application, but those are very typical for Erlang and Elixir applications, so we're not going to look at those too closely today. So let's first look at what goes into a service. So here's some code. Our service is just a module. That's easy. We're going to define one public-facing function, ping. So what are we going to do in ping? Well, the first thing we're going to do is just like a normal hash table. We're going to hash something, and we're going to get a number back out. And we're going to call that number our document index. That's just going to tell us where it goes in our hash table. the thing we're going to hash is going to be timestamp, just like I said. So it goes to a different place almost every time we run this command, because time is ever increasing. OK, and then the library we're going to use is going to be a RiakCore thing, but that's OK. It's hashing something, we get a number back. And we send this whole tuple, but that's not actually that important. So now we have a preference list. And so remember what I said, we did some transformation on the output of our hash function to figure out which bucket we were going to put our data into. And so that was modulo 4 in the case of our simple hash table. In the case of Riak, a preference list is all the vnodes that can handle this request, given the number, the position in the hash ring that we're going to. And so we're going to call a function called getPrimaryActivePreferenceList. And that's going to give us a list of vnodes for this hash number, the output of our hash function. We're going to look for a particular service on our hash ring. And so Chris was talking about service discovery, having multiple different services in your cluster. This is Riak's core version of that. I might have a different service. I might have 5 services. And so I need to specify which vnodes I'm interested in discovering when I'm looking for my preference list, or the vnodes that can handle the command that I want to send. We're only going to ask for one, because we only want to ping one thing. And we're going to use this RiakCore library to do it. We're going to unpack our preference list into an index node. That's just the actual PID. We're going to spawn command. We're going to send a command to this index node. That command is going to be ping. And we're going to send it to this named process, ping ring vnode underscore master. That looks a little funny as named processes go, but it's because RiakCore appends underscore master, and so it kind of breaks with the Elixir naming convention. Maybe I'll have a macro someday to sort that out. But OK, so that's the last thing we do. But the key here is that we're sending a command to a particular vnode, to a single place, and that command is ping. So let's look at the code that's going to handle that command. So the vnode, where we do our business logic. So again, a simple module. We implement the behavior RiakCore vnode. So there's a bunch of callbacks that we have to implement to satisfy that behavior. There's some boilerplate for startup. But then we have an init function, just like a gen server. Totally normal. We have some value. We return some map with some stuff in it that gets passed into every callback that we implement. In this case, the data we're going to hang on to as we do our callbacks is going to be the partition. And this is just the position in our hash table that this vnode is responsible for. So maybe our number is 2, and this vnode is responsible from 2 until 10. And so this partition is going to be 2, the buckets that this vnode handles. And then we implement a callback. We handle command for ping. And we just send pong back with our vnode ID, our partition. And then there's some other callbacks to satisfy the behavior. But that's the whole thing. So let's look at a quick demo. So I have 2 servers. Up top, I have server A, and on the bottom, I have server B. Server A is going to run a ping. It's going to take the current time to hash it. OK, this time it went to server A. This time it went to server B. I'll do it again. Server A. Do it again. Server A. OK? So that's how our ping service works. Those gigantic numbers are partitions. They are vnode IDs. They are positions in our giant hash ring. So that's cool. But what about state? I kind of promised that we're going to build a stateful application, not just a thing that pings, right? So let's build a second RiakCore application called storeFetch. And so this is going to be kind of predictable what it does. It'll store a key with some data. We're going to store the data in ets, so it's just going to be kept in memory. We're going to hash the key to figure out which vnode we're going to send our data to. And that's it. So let's look at some code. So here's the implementation of our service store, the kind of public-facing function. So just like with ping, the first thing we do is hash something to get a number, a position in our hash ring. This time, we're not hashing the timestamp. We're hashing the key of the data that we want to store. We're using this library, and it turns into a tuple, but that's OK. Once again, we take that number that our hash function output, and we ask for all the vnodes that can handle this command. So we got this number, and we said, hey, bucket number 2345. OK, great. I will send this to you. Once again, we're asking for this particular service. We don't want some other process doing a different service to handle this. And we're only going to store it in one place. And we're going to use this library. We unpack it. We get the actual PID to send the command to. We send a command to this PID. Our command is a little more sophisticated. It's a tuple with the key and the data, but very similar to what we were doing with ping. Once again, kind of funny process name, and that's the whole thing. Now let's look at our business logic, where we're going to actually store the data in the vnode. So again, behavior, some boilerplate. Our init is slightly different. We don't care that much about the partition, but we're going to instantiate an ETS table and then hang on to it in our state map. OK. Handle command, we're going to handle the store command. Key data, and then our ETS handle. This is very straightforward. We take our data and pop it into ETS. OK, that's easy. And then we're going to do the same thing for fetch, but we'll use lookup instead of insert. OK, we're done. We stored some data. We've distributed. This is great. But you might have noticed we're kind of only storing this in one place. And the thing about storing data in one place is that it's not terribly robust. The slow burn. And so the thing about storing data in one place is that we don't have reliability. We don't have fault tolerance for our data. If a single server goes down, we're going to permanently lose data because we're just keeping it in memory. So let's talk about fault tolerance. How many computers do you need for fault tolerance? Well, it's kind of an open-ended question, but basically more than one, right? Any more than one. So we're going to add a component to our RiakCore application so that we store our data on more than one server, on more than one vnode. So our write coordinator is going to do that for us. Instead of us directly pushing data to a vnode, we're going to hand it off to this process that's going to take care of writing it to multiple places, and then it'll tell us when it's done. So a write coordinator executes commands on multiple vnodes. That's it. The reason writing to multiple vnodes gives us some data safety, some fault tolerance, is that RiakCore takes care of taking vnodes that are placed in a row and putting them on physically distinct servers, on different Erlang VMs. So if I have vnode number 2, vnode number 3, vnode number 4, if I have enough members of my Erlang cluster, those vnodes will be on different servers. So if I write to 2, 3, and 4, my data is going to be on different servers. And we'll see this in a minute when we do a demo. So what does our service look like? Our high-level API, we're not going to be doing kind of that direct work anymore. We're going to be leveraging our write coordinator. So store key and data, just like before. We're going to introduce two new things, two new parameters, n and w. And so n is how many places do I want to store the data? If I do 1, this is just like I had before. If I do 100, then my data is very safe, depending on how many servers I have. W is the number of acknowledgements I must receive from the places I try to write to before I consider this write to be successful. So if I want to write it to 3 vnodes, I might set W to 2. So I'll write to 3 places, and then once 2 of them have said they've got the data, I'm good. I'll tell my user everything is cool. So let's do it. Store fetch, write coordinator, do it. This command needs to return a request ID because it's going to take some time. It can't just do it for it. We're going to wait for a message back from this process that will signal that we have successfully written to at least W things. So we get a request ID back. We'll use that later. The thing we're going to pass to our write coordinator is just like what we sent to our vnode before, because what the write coordinator is going to do is just send to some vnodes on our behalf, but it's going to manage some stuff along the way, and we'll talk about that. We're going to wait for a message back from our write coordinator. We'll time out after 5 seconds. And we'll do a selective receive on the ID that our write coordinator gave back to us. Once we get it, then we're good. Success. We have our data. It's written to multiple places. And then we have our fetch implementation. So what is the write coordinator? Well, it's a finite state machine. It is spawned on demand. So Jose was talking about dynamic supervisor stuff. Every time I am using my service to write some data somewhere, I spawn a new write coordinator to handle this request. Once it's done its job and written the data, it's done. It exits. So it's a simple one-for-one. And so since it's a state machine, I'm not going to show you code because that's just way confusing. I'm going to show you a diagram because that's what you do with state machines. So our state machine has 3 states: prepare, execute, wait. These steps are exactly the same as we did for our ping service and our store fetch service. So prepare takes a hash of our key and then figures out which vnodes are going to handle this command. Who is in our preference list? We transition to execute. We actually send the commands to everything on our preference list. That's easy enough. We transition to wait. And here, we wait. And that's the whole thing. And so once we've got enough responses from vnodes, enough acknowledgements that I have written the data, I'm safe, you're all set, we return back to whoever spawned us. And that's it for write coordinators. Now we are writing our data to multiple servers in our cluster. So if a server goes down, we still have it available somewhere else. Pretty cool. There is another major component of fault tolerance in RiakCore that I'm just going to cover quickly, and that's handoff. And so this covers the question of what if we add a server to our cluster, or one permanently leaves, or even goes down for a while. And so in that case, if we had a chunk of the hash ring that lived on that server, we don't want it to stay on a server that's down, because then that chunk of the hash ring is kind of gone forever. And so Handoff will take those bits of the hash ring and say, OK, this server's dead. Someone else can get them. And then they're going to be moved over there. It's implemented as a series of callbacks in our vnode module. And it's mostly just kind of some serialization. So I'm not going to really talk about the code there. So OK, now we have some fault tolerance. But you notice I haven't said a single word about Phoenix yet. Like I've been talking for a while. So let's get into talking about Phoenix. Surprise, buzzword. So Phoenix and RiakCore together. It turns out this is really easy. We just use an umbrella application. So if you're not familiar, you just have two applications in the same directory tree, and you do a little bit of configuration. And then your Phoenix application can use your RiakCore application like any other dependency. It's really cool and really straightforward. And so that's the entire process of putting these two really cool pieces of technology together. That's why I've got all this other stuff to talk about. So we're going to look at what this looks like. So we have some routes in a really simple Phoenix application. We'll put store key with some data, and we'll get store key, and we'll get it back out. And so this is going to send data to our RiakCore application and store the data on multiple vnodes, all that stuff we were just talking about. So the request looks something like this. We do a curl, with some JSON data in the body. And then at the end, we have my key. This data is stored under my key. So we're going to look at the code for a controller. Normal controller, my app, store controller. Define our store function. The first thing we're going to do is unpack the request body out of the connection. OK, I need the JSON that I'm going to store. And then our key from our URL. And now we have these two things. I don't write a lot of Phoenix code. If this is the wrong way to do it, someone tell me, please. So now we're going to arbitrarily set our n value to 3. So we'll just put it on 3 vnodes, 3 buckets. And then we ask our service to store our data on 3 things, and then return when you're done. And then we render it back out. And that's kind of the whole thing. We do something very similar for fetch. And so the major thing I want to emphasize about this is not that it's weird, but that this is pretty normal. That might be an ecto repo thing instead, right? Our controller is very standard. So OK, let's look at actually doing stuff. So OK, I've got 2 servers. In the middle, I have server A. On the bottom, I have server B. On the top, I'll have my client. And so we're going to first put some data into our application, and then we're going to take some out. So we'll store under the key Brussels some JSON food equals chocolate. OK, great. And so we can see 2 of the vnodes we're storing to are on this server, and 1 of them is on that server. Great, fault tolerance. Yeah. So let's do a different key. Clear that out. And this time, we're going to write some different city, maybe the one we're in. And our food will be something different, like currywurst. And this time, 2 of our vnodes are on server B, and 1 of them is on server A. So cool. So we've distributed our data. We do different keys. They end up in different places based on the value they hash to. And let's fetch our data back out. So we're going to go ahead and grab Brussels. And we can see it's served by the place where the vnode was residing on server A. We'll do the same thing for Berlin. And pow, same thing. So our Phoenix application fetched that data from server B, presented it to the user, and we're done. So this is kind of a model of a database-free architecture, or kind of like your web server and your database are in the same place, which is really kind of funky and maybe scary, but cool. So, OK, Phoenix. What about real-time? What can we do there? Can we do something cool? So obviously, if we're going to do something real-time and we're talking about Phoenix, we're talking about channels. And so if we want to do something cool with Phoenix channels, we need something to hash on. We need a key to manage our value, where our value might be a message. Well, here is what the struct for a message for a Phoenix socket broadcast looks like. And you kind of look at it and you go, OK. Oh, what's that? Right? Well, the topic looks like it might be the perfect thing to hash on. So let's do that. I did it. So let's talk about a pub sub adapter. I wrote a really simple pub sub adapter. It's totally just a hack, but it was kind of fun. And what it does is take the topic of the channel message, hash it, and decide which vnode in our hash ring should handle this message. And what that means is that this vnode manages the subscriptions and broadcasts for this topic. It's really cool, by the way. And so what that means is that you've sharded responsibility for your channel, for your topics across your whole cluster. So rather than every node in your cluster getting every message for every topic, when you send a message, it's directed to a single place, and that place manages the subscriptions for that topic. Kind of cool. OK, so here's the pub sub adapter. It's got 3 functions: subscribe, unsubscribe, broadcast. I didn't do the more sophisticated things because I was in a hurry. And this is really simple. They're just trivial wrappers around our service. By the way, our RiakCore application is called PubRing because PubSub and hashring and put those things together. So what does the service look like? Well, it's kind of like the other services we wrote, the ping and the store fetch. So the first thing we'll do is hash the key. That is our topic. We get a preference list, the vnode, where we should send this message to. And then we send the command to that vnode from the list. And that's it, just like the other thing. So because it's so similar, we're going to jump straight to the business logic, because the high-level API is the exact same process that we've already done a few times. So what is our vnode doing? Once again, we have the behavior RiakCore vnode, and we're going to skip the initialization and stuff and look at the 2 callbacks for subscribe and broadcast. Unsubscribe is just like subscribe, just kind of backwards. So we're not going to look at that one. So the first thing, subscribe. This one's easy. We get a PID and a topic. So this PID should receive messages for this topic when they show up. Well, we put it into our ets table, and then we return. Ha, done. OK, so we're keying it on topic, so we know that this PID should only receive messages for this topic, because this vnode might handle messages for different topics, because it just depends what they hash to. And this vnode is responsible for multiple chunks of our hash ring. So OK, now let's look at broadcast. Broadcast sends a topic and a message. So I'm a member of this channel or this topic, and I want to tell everybody some message. The first thing we do is pull out all of those PIDs who should receive this message from our ets table. We're using match syntax. It's a little funky, but we pull them out. And we take those PIDs, we go over them, and we send them all a message. It could probably be faster if we did some cool concurrency thing here, but I'm just iterating over them sequentially. That's fine. And we send them a message. And that's the whole thing. And now we've broadcast a message. So let's look at how it works. OK, so I have 3 VMs, 3 servers. And I have 3 clients. Each one's connected to a different server. This is so you can see that I'm not just making things up, and the messages do actually go from place to place. And so lobby messages are going to hash to this server. Private 99 messages are going to hash to that server. Don't worry about the text. It's tiny. I'll point stuff out. It's different colors, too. So the first thing is I'm going to write a message to lobby. Foobar, and OK, it replicates the other clients. Good, I've made the basic requirement for PubSub, and the message only hits this server. I do private 99, it's the same thing. Message only hits that server. Another message to lobby. By the way, this client is connected to this one, and this one is only forwarding things to my hash ring. It's not managing any subscriptions. It's not broadcasting any messages. Yeah, so that's kind of neat. That's my PubSub adapter. So this PubSub adapter is basically just a really complicated version of PG2. It doesn't provide any major benefits, but we could do something really cool with state. So because we've distributed responsibility for topics around a whole cluster, we have more resources we can invest in a given topic. And so we might do something really cool. It could be just keeping some message history, but this could be something like game state, like we heard Keith talking about, where we were doing game state on the server. Now that's going to be really challenging if we're doing it on a single server and we have tons of different games going on. But now we have a mechanism to distribute this game state around a cluster in a structured way. That's really cool. This is a superpower. This is a big deal. It's cool. OK, so real time. We've got one last thing on our checklist. Impress your cat. Sad face. Not going to happen. OK, so. Sorry, was I too quick? I jumped. Yeah. OK. So what else is going to happen here? Well, I think this is a really powerful approach. I think that this isn't right for many applications, but when you have something where you have a data set you could fit in memory, but more than on a single box, I think it's a really powerful approach that we could do a lot of really cool things with. So I think it should be easier to build these things. So maybe we'll make some scaffolding thing. Maybe the scaffolding thing will let you also include a Phoenix application in your hash ring. Maybe it'll generate a write coordinator, because those are pretty straightforward and pretty much always the same until you get into fancy stuff. Maybe we'll have a macro, so there's less boilerplate writing vnodes. And maybe kind of a more serious implementation of the PubSub adapter I made. And who knows? But it's cool stuff. And I think there is a lot of potential for people to write really cool applications using this approach. So thanks very much. I really want to thank the people who have put content in the world for learning about RiakCore. Mariano Guerra has a whole book about this, and it's wonderful. Mark Allen has given great talks and has a really excellent example application. Ryan Zazeski, same thing, great blog posts. And then Project FIFO for having a fork of RiakCore that compiles on Erlang 18. That was important for this talk. And then the source is actually really well commented. So that was great. So thank you very much. That's it.
So, yeah, that's the first question. No, this is why not cool.
So
Hey.
Nicole mentioned earlier that you could maybe enact or separate the data from the database. Is this something you could maybe start doing in Ecto?
Yes, in theory. I'm not familiar with how Ecto adapters work, but I think in principle there's no reason why you couldn't hide that RiakCore service, the high-level API, like just storing and fetching stuff, or whatever other semantics you implement behind an Ecto adapter. That'd be really cool. Yeah.
Am I right in understanding that this is just in memory? And if that is so, how do you add persistence to this?
Yeah, that's a really good question. So, of course, when you're using real Riak, it's not just in memory. And so they use LevelDB for that. So you kind of get both memory and disk persistence. The fork of RiakCore that I'm using, Project FIFO, actually inputs RocksDB there instead, which is Facebook's kind of in-memory but persisted data store. And so basically, instead of just using plain ETS tables there and kind of putting things in memory, you would use something like LevelDB or RocksDB. So you could kind of store things in memory and have them written to disk as they come in. So that was mostly for the talk. It would be pretty straightforward to persist things, I think. So.
How does data get distributed? If you have a new server, can it be moved around?
Yeah, so that's a really good question, and that's what Handoff is. And so my cluster has 3 members, and then I add a 4th. Well, at some point, RiakCore will gossip information about its state to each other, and they'll go, hey, we've got somebody new who's joined our cluster, and they're not doing any work. That's not good. So they will reallocate some of the vnodes from the existing cluster over to the new one and kind of rebalance things. That sounds a little scary because it means shuffling a bunch of data around depending on how much data you have. So RiakCore uses what's called consistent hashing so that not all of the data has to be moved. In a normal hash table, when you resize it, typically you move all the data. But in consistent hashing, you only have to move some proportion of it. So yes, it moves it around using Handoff.
Okay, fantastic. Thank you very much.